something you may want to take note of if you were confused by that example. And the other thing that I explained, but only to those who were here, was kind of a bit more about this proof-finite completion bit, so don't worry too much about it. If you know everything about it, it's good, and if you don't, then it will not deter you, at least in this lecture. And I added here, so this was also good. So I said that, okay, now we may as well restrict to gamma, to finitely generated groups gamma, which are also residually finite, and the definition is still here. And so you may wonder, maybe now I'm losing my favorite group, right? And so if you're interested in infinite simple groups that are finitely generated, then yes, you've lost. But so if your group is linear, then you're okay. I mean, so in particular, we have a large class of groups. So every linear group that's finitely generated will satisfy this kind of requirement. Okay, so that's just it's not an equivalence, but it's somehow, maybe it's reassuring to know that we are talking about groups that are a bit more general than linear groups in this kind of finitely generated setting. Okay, and the rest are things that I kept because I wanted to refer to them. Okay, so the next thing I want to do is I want to go through these examples again. And the first example I mentioned, well, I briefly mentioned, was this example, the Abelian case, right? And Christopher already told us about that. And I want to do that in a slightly kind of more algebraic way. To draw a picture, because I don't get occasions to draw pictures very much, and because when we want to do maybe the Heisenberg group or kind of higher Heisenberg groups, and that becomes quite difficult, then these kind of pictures might be useful. So it's a simple example which hopefully gives us some ideas what to do if we encounter slightly more general nilpotent groups. Okay, so examples. So one, we're going to look at gamma, just the free abelian group on D generators. And we've already shown the subgroup zeta function. And so what we can do to analyze this algebraically is the following. So where we pick a free generating set, so I will call my generators x1 up to xd. And now I want to work by induction on D, right? So if D is equal to 1, then I guess we all know the answer, and this is this Riemann zeta function that surfaced before. So for every index n, there's precisely one subgroup, namely n times z. And when we care to form a kind of Dirichlet generating series, which I haven't written down yet, but which was in the first lecture by Christopher, then you get the Riemann zeta function. Okay, so now we do induction on D. And so to do that, we pick a normal subgroup lambda, which is of that kind. So we just split off the last generator, right, xd. And so if I want to count things, I can do that using the following picture. So up here is my group gamma, and here's my fixed normal subgroup lambda. So this is fixed, so let's make it a solid block. And I'm trying to count these deltas, right? So I have subgroups delta that I'm trying to count. And there are two kind of relevant groups that I can look at. I can look at what delta and lambda generate together. So it's an abelian group, so this is very easy to do in some sense, but in general, this also makes sense if this is a normal subgroup. And we can look at the joint, so we can look at the intersection of these two. Okay? And from first year kind of group theory course, we know that these indices are the same. Yeah? Okay. And so we're interested in things that have index n, so we're trying to count subgroups of index n. So let's give this a name. So this index here I will call m. So it's the index of delta in delta lambda. And then, of course, the rest, I mean, the remaining index here has to be m divided by m. Okay. And so this picture yields the following. So this yields the following recursive formula in some sense. So the number of subgroups of index n in gamma, well, I need to run over all possible m's, and the m's are the divisors of n. So I need to run over all m's dividing n. That's a finite sum. Then I need to work out how many possibilities do I have for this join up here. And that is a subgroup of index n over m in this quotient group gamma modulo lambda, but that is z to the d minus 1. And so by induction, I'm not scared of it, right? I know how to do that. So that's very, very, very good for us that that's possible. So this is gamma modulo lambda. And we know this thing, so this is s mod to z to the d minus 1. And then I need to count how many possibilities do I have for this group here inside lambda. So this group here, it's sitting down here. How many possibilities do I have that inside lambda? And lambda is just z. So there's only one possibility, right? It's index m. So I have to multiply this with the number of possibilities that I have down there, but that is just equal to 1 because this group here is z. Okay, so that disappears completely. And then we have to work out, well, once I give you these two groups together with lambda, how many possibilities do you still have for delta? I'll explain that in a little while. It has to do with derivations. But that turns out to be, in this case, it turns out to be m to the d minus 1. Okay, see below. So see below. Or see to the right, I don't know, wherever it appears. Okay, and so, and this, yeah, this is known by induction, so this is known by induction. So we were very lucky that somehow this group and also this quotient group somehow fit the picture, right? They fit into the family. This will never happen again. I mean, this is like your birthday, or your 20th birthday or something. Now you feel strong, yeah? And then when you turn 40, I don't know, something else happens. But this is a one in a lifetime. And then, I mean, this gets quite complicated in general. This is very nice. I mean, this looks really nice in this setting, but somehow this gets complicated. So all three ingredients happen to kind of be very nice in this situation. But in general, this might be a strategy, but not a strategy that will always be successful. Okay, if you wanted to imagine this in terms of matrices, in the style that Christopher maybe sort of indicated, then I can also draw a picture. So imagine that in my rows, I will record generators for my subgroup delta, and I will sort of place my generators on the top, kind of in the columns. I will sort of look at the coordinates in terms of the generators for gamma that I've picked. And so what I have to do is I have to sort of pick some smaller kind of matrix that represents this subgroup modulo, this subgroup here, modulo in gamma modulo lambda. That is basically by induction. This block here, I fill in by induction. And down here, well, there's only this one choice. I put m, right, because this is z, and this is mz. I mean, this is in terms of xd, that is mz. So I put m there. And then, of course, I can fill this in as I want, modulo m, and that gives me this. This gives me this contribution, right? That is actually the kind of number of complements that I have. I mean, in terms of matrices, this is kind of easy to picture. And the induction sort of takes care of that bit that I don't know how to fill in. Okay. And now in general, I mean, in general, how does one do this in general? I'll try maybe what machinery do we have? So you need to work with derivations or one cocycles. So you see, we have this normal subgroup, lambda, and we have an action of our group. And in our case, because lambda happens to be kind of central, it's actually an action of gamma modulo lambda somehow. So this also makes life a bit easier. But in general, the problem is the following. So it reduces to, so in general, it reduces to the situation where you consider a semi-direct product. Yeah, so in my case, the group G is basically this part here. This is this modulo that. That is my group G, and this is my normal subgroup, and I'm trying to count complements to that normal subgroup. Yeah, this is this setting, and you have to reduce to that. It's not always going to be the case that, that this, you can mod this out, but okay. You can reduce to this setting. And so in this situation, what is the number of complements to n? So the number of complements, such as h, so we're looking for brothers of H, complements to N in G. There's an algebraic theory for this. So this is the number of derivations from H to N. And what are these derivations? So they are one cocycle. So they are maps delta from H to N, such that if you take any two elements, X and Y, in H, then delta of the product, X times Y, is delta of X conjugated by Y, or if it's a module, this is the action of Y on the module N, times delta of Y. So these are one cocycles. These are kind of derivations of one cocycles. Derivations or one cocycles. And you may have encountered them in this situation where this is like in a abelian group. I mean, like where there's a module. And this works also in the non-commutative, in the group theoretic kind of setting. Okay, and what is the complement in this case? So the complement is H delta, which just consists of all elements like this. You shift every representative H by a little bit inside N, and this is your complement. Yeah, this is the connection. There's a bijection kind of in these terms. Okay, and so in our case, because our module is central, this action disappears, and we just get homomorphisms. And so we just count homomorphisms from this group, which is again, from this group, which is again Z to the D minus 1, because every subgroup of finite index is again Z to the D minus 1, into Z modulo M. And so you choose for every generator what you want, and you have M choices, so you get M to the D minus 1. Yes, so in our case, the derivations from Z to the D minus 1 into Z modulo MZ, these are just homomorphisms. And there are M to the D minus 1. And that's what we thought in terms of this picture anyway, what I wrote here. Okay, so so that's nice, and still it's a mess because now we have some recursive formula, and who wants to actually evaluate these things and get formulas, and so that's where the kind of zeta functions kind of come in. So it's a good idea to look at a generating function, and because somehow if you stare at this recursive result, or if you some previous knowledge, there's some multiplicativity, and because we have this multiplicativity, it is a good idea to use generating functions that are Dirichlet series. Okay. And so I'll just recall the definition that was given already by Christopher. So it's a good idea to organize this in a Dirichlet generating series. And so this is the subgroup zeta function of gamma. And you just form formally the sum n equals 1 to infinity, an of gamma n to the minus s, where you think of s as a complex variable, but you can also think of it as a formal parameter. Doesn't matter at this stage. And what's crucial is that these are finite. Yeah, I mean, some of the coefficients are finite, and that was true for any gamma. And so another way, suggestive way to write this is you run over all finite index subgroups, delta and gamma. You determine the index. You count this one with that particular weight, so you can write it like that. That's another way to write it. And this way suggests that, and that was, I guess, the motivation also partly in the old days, like 30, 40 years ago, this looks very similar, so it's reminiscent of the Dedekind zeta function of a number field. So Dedekind zeta function of a number field. Okay, so what is this? So this is the sum. I mean, there are many different ways to write it, but one way to write it is that you go through all the ideals of the ring of integers of your number field K, and with the ideal norm, you weigh this, but the ideal norm is nothing else but the index. Yeah, as a group theorist, I mean that is the same as the index as an abelian group. All the ideals, the non-zero ideals in the ring of integers number field have finite index, and that is the ideal norm. And so it is exactly the same formula as here. And so if you think of finite index subgroups as taking the place of these kind of ideals, non-zero ideals, then this should be sort of, I mean, there should be some kind of inspiration coming from the right, or maybe some, warnings. You shouldn't try and prove the Riemann hypothesis in a more general setting. I mean, good. Okay, and here in our situation, when we play this through, we get the formula that Christopher kind of mentioned. So here, in this kind of particular setting, we obtain just the product of shifted Riemann zeta functions, I equals 0 to d minus 1, or maybe k is a better parameter. Riemann zeta function s minus k. And then somebody mentioned this in the break. Then what is it good for? So there are some kind of, this is now a complex function. I mean, now the Riemann zeta function we know. So this is a complex function. This is a complex function. And it's actually an analytic function for a right half plane, namely the pole. I mean, the danger spot is at s equals 1, right? So this is it's okay for real part of s greater than d. And it actually has, I mean, we know that the Riemann zeta function has some kind of meromorphic continuation. So the picture somehow to draw is like this. So there's this half plane. This is this kind of right half plane on the complex numbers. And actually my function can be extended. And then the general theory says that there must be, I mean, there could be maybe other, but there must be a pole here on the real line. And so one can investigate this pole. I mean, it's very easy to do. And then using the pole order, one can get very precise estimates now about the number of, so there's some kind of general machinery developed by people in the 19th century or something, which says that asymptotically, if we're interested in the number of subgroups, then this is asymptotic to n to the, so in our case, it's alpha of gamma. So this alpha of gamma here is, so this is called alpha of gamma. Times, and then there could be a log term here, which somehow here disappears because we have a pole of order 1s. But in principle, there could be a log term here, and that is related to the kind of the singularity, type of singularity that we have at that point. And asymptotic means that if you take the quotient of these two things, you go to 1 as n goes to infinity. So this is in the precise sense of number theory. So there's some tools, some general machinery, some Tauberian theorems that, okay, we can just use for free in some sense once we have a nice formula for our subgroup zeta function. There's also a constant, you're right, sorry. There's also a constant, which if this means what I said, there should be a constant here. And this constant somehow is also supplied in terms of the gamma function, in terms of special values of the gamma function and maybe the zeta function in our case. So there's something we have to compute. So I guess for d equals 2, it's something like pi squared over 12 or something. I mean, you can give it names if your group is really nice. Okay. Right. Okay, so let me just say that what I just discussed, I mean, this was an example, but this kind of setup with this kind of, that these things converge or something, this is general Dirichlet series business for Dirichlet series with non-negative integer coefficients, at least. I mean, it's also slightly more general. And so in general, there's a difference between absolute convergence and convergence. So here's the same. And this invariant alpha gamma, maybe I should write down the formula once. We saw a similar formula before. So this alpha gamma is just the one that picks out the polynomial degree, as we see here. I mean, this is the polynomial degree, really. So alpha gamma, maybe I should put a less or equal because it's for subgroup growth. So this is the lim sup of the log of Sn gamma divided by log n. And this is called, so this is the degree of polynomial subgroup growth. And in terms of Dirichlet series, it's abscissa of convergence. And the alpha is is one of the standard terminologies for these abscissa, and that's where it comes from. It's called alpha of, because it's the abscissa of convergence of this associated Dirichlet series. Okay, so that's the first example. So let's look at the second example. This was this Heisenberg group. So the definition of the discrete Heisenberg group is still here, and I mean, this was the algebraic kind of maybe raison d'etre for this kind of example. That's kind of some free nilpotent group, so it should be kind of the next thing maybe to look at after we did free abelian groups. And so this zeta function has also been computed, and I guess we could do that. We could do that in the tutorial. And so here, one of the a key ingredient is this multiplicity. So key ingredient is the fact that so here's now gamma, look at this example, that the subgroup zeta function of gamma allows for an Euler product. So first at the formal level, and then as for the Riemann zeta function, you can check that it also kind of, on the region of convergence, that it gives you actually a product of complex functions. And there's this kind of local zeta functions, so one for each prime. So we throw some of the complexity into the distribution of primes, and we let that complexity for the number theorists to deal with. Yeah, we're not going to try and say anything new about that. At least I'm not going to try. You might, but I'm not going to do it. So this is really like one reason to focus on this, because there might be something that we don't want to try to do. And so the definition of these local things is just you count only subgroups of index a power of p, of your prime p. So you only count the subgroups of that given prime power index, p to the k, and you supply it with the usual kind of n is now p to the minus k, so n to the p to the k, n to the minus s is now p to the minus ks. So it's the usual kind of treatment, and k goes from 0 to infinity because we have p to the k. This is just exactly what we did before. Just we're focusing on that one prime. And this, okay, this was mentioned, but this maybe requires some explanation. So this is essentially, this is just the fact that in a finite nilpotent group, so a finite group is nilpotent if and only if it is the direct product of its Sylow of p subgroups, yeah? And only if it is a direct product of its Sylow subgroups. One for each prime, of course. I mean, otherwise it wouldn't work. Yeah, and the reason is, okay, we have this group gamma. We're trying to count things kind of close by, a finite index here. So whatever we're trying to count, there are finitely many things of index n.
So let's take the intersection of all these things we're trying to count of index up to n. So that will be a normal subgroup, a lambda, and it will still have finite index. And so as well, I mean, instead of counting things inside gamma, I may as well count things inside G, which is gamma modulo lambda. And then I have a finite group, but it's a direct product of its CELOF P subgroups. And so the subgroups are just a direct product. I mean, that's true also for every subgroup because nilpotency is inherited by subgroups. So that means that counting things inside a direct product of different P groups for different primes P is the same as counting in each factor and then forming the direct product again. So this is the reason for this kind of formal or an analytic Euler product. Okay, so for nilpotent groups, this business is very nice. In particular, it happens here, and then I guess this was computed around also 1980 or something. One can, in a similar way as described here, but slightly bit more work, one can work out the subgroup zeta function for the Heisenberg group, and it turns out to be almost of the same kind. But if you then go to the higher Heisenberg groups, you see that somehow, okay, things become more interesting or more complicated than just studying products of shifted Riemann zeta functions. Yeah, I guess that was. So this example was good in the sense that people thought, this is beautiful, let's study it. But it is not, I mean, it's just the beginning of some story. So, so the subgroup zeta function, I wrote this down here, hopefully, well, someone in the audience will sort of know this by heart, but of course I don't, so I'll copy it. So it's the product, turns out to be a product of shifted Riemann zeta functions, 2s minus 3. And then there's a little trick, some people did that. There was another factor which didn't look like a shifted Riemann zeta function. And so they discovered, we can just sort of, we can get it to change a little bit. And so we just divide by 3s minus 3. So maybe it's not a product, but it's a quotient of shifted Riemann zeta. But that's sort of a bit deceptive because this is sort of like a little trick you can do here. But in general, somehow this is not what you should expect, I guess. So, okay, it's a bit misleading to write it like this, but still it looks beautiful. Okay, and so if you now ask, okay, what's the degree? So we can now ask, what is the degree of, and that's something we could compute later in the tutorial. I mean, this is not too hard. What is the degree of subgroup growth? Well, you will have to look at where the pole is. There's an abscissa convergence of this thing. So where's the pole? You'll discover that here, this factor, for instance, for s equals 2 gives trouble. And this factor also for s equals 2 gives trouble. And the other ones are fine for s equals 2. I mean, the other ones, they give trouble further to the left. So this, okay, what is like this. This happens to be 2. And the pole order is now 2. And so this kind of asymptotics that I described earlier for the Heisenberg group, and I think I wrote the constant here. Yeah, this leaves, so there's this constant that Christopher referred to, so it's pi over 4 divided by 72 times zeta of 3, if I did that correctly. Then there's the n squared, so that is because this is this 2 coming up here, so this is the polynomial degree. And then because it's a pole of order 2, there's another log factor that we can actually also give, and it's 2 minus 1, which happens to be 1. So it's just log n. Okay, so you get a very fine asymptotics for the distribution of these. And that's maybe not the perspective that we are going to take this week, so these combinatorial things. And yeah, how did this come out of this machinery? What was the local factor that sort of went into that Euler product? So let me write that down as well. So from a local perspective, so for prime p, the zeta function, the local zeta function, happens to be 1 plus p times t plus p squared t squared times 1 minus t times 1 minus p squared t squared times 1 minus p cubed t squared, where t is to be evaluated at p to the minus s. And you see some of these factors, like this one. This will give you this Riemann contribution here. Yeah, and you can match these two as well. And then you see this strange thing. But then, yeah, luckily somebody thought about multiplying this by 1 minus p times t to get sort of this thing, and I guess this thing, these two things together, I guess. They give you that contribution here. And there's a bit of a kind of trickery, right? Okay. And 36, you say? I could be, I don't know. You did in your head, yeah? Okay. I don't know, maybe 36. Okay, let's record this here. I won't vouch for it. It's, you probably know it better than I do. I didn't compute it again, so I computed it some time ago, and I may have made a mistake. Okay, right. Okay, let me flash at you. How much time do I have? Another 15 minutes, or what is it? 15 minutes. Okay, let me flash at you the formula for H2. I will not show you the formula for H3, because Christopher told me it's horrible and it's hidden in some folder that he has at home or something. So H2, recall, it's this group. I mean, we might now feel in the position to do a few more examples and then prove analog of Bass' theorem, right? Like Bass gave me the degree of growth. I mean, I want this formula, sum Ri times I. I want to figure out what that could be. And so, so here, this zeta function, it starts like this. So if you look carefully, you will see that this here, is it okay to box it like that, or should I get color chalk? Okay. This is just the subgroup zeta function that we got for z squared. Okay, it's not surprising that this sort of shows up because the factor, the Bielization of my Heisenberg group was z squared. Okay, but somehow we wouldn't see it, and we would expect it as a summand rather than as a factor. I mean, why should there be a factor? It's a bit strange. It's like, I mean, so in some sense, it's a bit deceptive. But anyway, if you compute this one, apparently you get the zeta function of z to the 4. You might have, well, z to the 4, it's like here, it's again like the Bielization coming from these kind of things. And then you get it as a factor, and there's some shifted Riemann zeta functions. So the shifted Riemann zeta functions are 3s minus 4, 3s minus 6, and 3s minus 7, I guess. And then there's something that is a bit like this, but getting more complicated. So I'm writing down the global thing. So there's a product over all primes. And the thing you get is of the form 1 plus p to the 5 t cubed minus, so there's also some negative signs coming up here, p to the 5 t to the 4 minus p to the 6 t to the 4. And it goes on and on. Let me not write all these terms. But so there are 4 or 5 more. So at the end, you get a p to the 13, t to the 8. Okay, and again, t is p to the minus s. Okay, and then there's a similar thing for H3. And okay, this was done by me and Christopher somewhere around 2006 or 7, or I don't know. It's a long time ago. We did some calculations. So there's a similar kind of formula where this polynomial in P and T, well, it sort of becomes a bit bigger, but it's kind of, it's still a polynomial. Okay, and so I think the method we used was some kind of using buildings or something, but then we felt so exhausted afterwards that we didn't write a paper and we kind of got lost. But there's a conjecture coming out of this. So if you look at this formula, and then the one I don't show you, okay, this part looks increasingly kind of complicated, but this beginning part, this looks quite nice. So that's this beginning part here, I guess. And so you can easily make a conjecture what that should, sorry, it's not, I kind of circled here because, okay, I forget about it here. I mean, it's this part, sorry, this part here. So that's reasonably nice. And so there's a conjecture or question, and nobody knows, or at least I don't know anybody who knows. And you might be the first person to prove it. That for these higher Heisenberg groups, it's always like this pattern persists. So conjecture, question. So if gamma is Hn, so this is a group of Hirsch length 2n plus 1. So the center is z, and then on top there's something that looks like z to the 2n. This is what it looks like. Okay, and it's given explicitly in terms of these matrices with integers in the first row and the last column and zeros elsewhere and ones on the diagonal. So this should be maybe always the zeta function of the Bielnization times the product. And since you are in the workshop for combinatorics, you've worked it out already, and it took me much longer to work that out last night. N plus 1 times S minus 2 n plus n choose 2 minus j choose 2. Minus j choose 2. So again, this is a shifted Riemann zeta function where now a is n plus 1 and b is this integer here. And then there's the kind of more interesting or more difficult part. So I will not say anything about that. So times a product of polynomials Wn in P and T, so let me write P to the minus S directly, where Wn is a polynomial in X and Y, and by theorem of Christopher, and I don't know whether there's any other way to see it maybe for these examples, but I don't think so. We know precisely what the degree is. I mean, we know these numbers. So these numbers here are not mysterious. Yeah, these numbers kind of, at least for almost all primes. So, okay, so there might be some kind of complication hidden in that we cannot quite guess how. So there's part of the conjecture is that this depends polynomial kind of on P, and the general theory doesn't tell us that it does. And the general theory does not quite give us an explanation what the degree should be, but the degree, I mean, there's a conjecture, I mean, it is known, if the conjecture is true, then the degree of Wn is known. I mean, it's known. It's known by general theory if the conjecture is true. If the conjecture is true. It's predicted by this kind of, what did you call it? Reciprocity or something. Yeah, there's kind of an inbuilt reciprocity in that we know holds true, and yeah, it's a challenge to maybe for these higher Heisenberg groups to kind of produce something like that. And in particular, we don't know. I mean, we don't know. I cannot say anything about the alpha because the alpha may as well come from here, right? So I don't know. Okay. So let me be quite quick on the remaining things so that tomorrow we can get to representation growth. So this kind of group, you can do subgroup growth, and it is non-polynomial. And that's not a big surprise because it was non-polynomial kind of for the word growth as well. And so slightly easy exercise that we could do in the tutorial is one can prove that ak 2 to the k plus 1 is at least 2 to the k squared. Yeah? And then you see that somehow the dependency, this is not, it's not polynomial in that, right? Because if I don't know, square this, I will get something like 2 to the 2k rather than 2 to the k squared. Right? So this is not linear in k. I'm saying k squared is not linear in k. And the reason why, I can tell you what the reason is, and then we can discuss it in the tutorial if you want, is you look at the quotient, finite quotient. I didn't write here, but okay. You look at the finite quotient c. I think it helps to do c to the 2k. So you look at the quotient where then you see a finite reef product with a fat thing here. So there's a finite quotient that basically is of the form c2 to the k reef, sorry, c2 reef, c2 to the k. And in that finite group you count, and then you get this bounds, and you can sort of see it's okay. And I'm not sure whether the precise kind of growth is known. I don't know, I didn't find anything. And then of course one can look at the free group, which is still here. And this is also instructive. We are not going to study it, but remember the word growth was exponential. And here it is known, and it has to do with enumerating transitive permutation representations and their results by Marshall Hall and Morris Newman. And so here, AN of gamma, now my group has become gamma, is asymptotically the same as counting, this is another variant that we don't have time to discuss, but maybe next week somebody will mention it, maximal subgroups. This is related to probabilistic kind of phenomena in the group. Sort of like if you don't generate a group, you're inside a maximal subgroup. So it's interesting to count how many maximal subgroups there are of a given index because it relates to some kind of probabilistic kind of group theory. So there's as many, as I'm talking, there's as many maximal subgroups in a free group as there's subgroups altogether. And the asymptotics is super exponential. So it's n times n factorial to the d minus 1. Yeah, so that means, I mean, this is a bit like n to the n, which is a bit like 2 to the log n times n. So it's log n and not n in the exponent. So it's super exponential. So it's somewhat faster than exponential. Okay, but people have concentrated more on the small side of things, and maybe that's a good thing to mention at last. So we had Gromov's theorem characterizing groups of polynomial word growth. So there is a characterization of groups with polynomial subgroup growth, both in the profinite setting, kind of larger kind of setting, and in the setting that we're looking at finitely generated groups. And so the theorem, relevant theorem, is the following. So this is due to Alex Lubotsky. It's a combination. I mean, the paper is really short. If you look it up, it's very short because basically they just string together a series of previous kind of results that they, especially Lubotsky and Mann sort of had before. So, so it's 1993. So if gamma is a finitely generated residually finite group, so residually finite was this technical term that we need to introduce because there might be God knows what hiding underneath. So then gamma has polynomial subgroup growth. So this means that this abscissa of convergence of gamma is finite, and we can study the subgroup zeta function. This is true if and only if gamma is virtually solvable. Okay, so this up to finite index is solvable, but it's not of that kind. So it is of finite rank, so a finite prefer rank. So it is more general than the nilpotent. So there are more groups of polynomial subgroup growth as compared to of polynomial word growth. But we need some finiteness condition, namely we want to be of finite rank. And this is equivalent to, this was known, but I'll write it because that might be more familiar terms for you. Gamma is virtually solvable and linear over Q. Q. And this theorem, uses, many ingredients. It uses a particular tool that is very useful. It's called the Lobotsky alternative, kind of an analogy to the kind of like TITS alternative or sort of other kind of landmark results like that. So the Lobotsky alternative says basically that certain kinds of groups, they're either virtually solvable or they basically see as many subgroups of finite index as sort of some arithmetic groups see congruent subgroups or some simple algebraic groups. And those were counted, and they have more than polynomial subgroup growth. So if you have polynomial subgroup growth and you then are in the position where you can apply this alternative, you know that you have to be virtually solvable. This is kind of like one of the big ingredients. And behind the scenes, use something like the classification of finite simple groups and the Phi-Thompson theorem anyway. And you use a lot of big machinery that goes in this. This is not a result that is a self-contained proof. And so this uses certainly classification of finite simple groups. So you may or may not like that, but it's not just means that you will not understand the whole proof, I guess. Okay. And I didn't say what rank is, so this means that important definition. So there exists some number R, this is the rank. Well, the smallest such number is the rank, but there exists a number, and you take then the smallest one, such that whenever you have a subgroup delta of gamma, infinite index or finite index doesn't matter, it's finitely generated. You see, here, in this example, we had a subgroup, namely this huge thing of C2s on the bottom that was not finitely generated. So that you now look at all the finitely generated subgroups. So where's it gone? Here. If the number, this is my notation for the minimal number of generators of the group delta. So if this is finite, then actually, you only need R. So this is the definition of finite rank is there is some R such that whenever you're finitely generated as a subgroup, you are generated by at most R elements. And the smallest such number is called the rank, the prefer rank. And that is the kind of finiteness condition that needs to go in there. And I think my time is up, so I can tell you what I would have done if I had had more time. But that's something I can discuss also at the beginning of tomorrow's lecture or in the tutorial. So there's a version, a local version. We saw that we're interested in like this kind of local fact for nilpotent groups of these local factors, like kind of at the prime P. And so part of the proof or the scheme of proofs or the idea of the proof is that there's a version for not pro-finite groups, but pro-P groups. Pro-finite groups that have the property that they're inverse limits of finite P groups. And there's also characterization. It's much easier for polynomial subgroup growth. And it says those are the ones that are p-adic analytic. And that's a nice class of groups, and it includes a lot of groups that are not nilpotent. Like SLNZP or things like that. And so it's very difficult, apparently. We don't know how to develop, let's say, the theory of zeta functions or abscissa of convergence or anything you want connected to subgroup growth for kind of compact p-adic Lie groups of simple type. SLNZP. This is not known. And that this proof that this characterizes these groups of p-adic analytic groups, this one can sketch. I could have sketched if I had another 10 minutes or so. Yeah, so the local version is kind of, it's nice. It's like group theoretically kind of accessible. As this global version, uses deeper results. Okay, thank you. So. I don't know. Presumably you would need, you would need to know. So there are groups that, so the subgroup zeta function of of this group that we saw is the same as the subgroup zeta function of the fundamental group of the Klein bottles. So the semi-direct product where you act like multiplication by -1. So there are non-isomorphic groups that are isospectral. So this seems to suggest that if you want to somehow prove that, I mean, some abstract groups are the same just because they sort of have the same subgroup growth, this is not going to work on the spot. But maybe in some classes you might be able to do, yeah. Yeah? So this is an exercise. This is a good exercise. Like we did this, and to convince oneself that actually this group has the same, it's because very small, but you can make many examples. Like, so they're isospectral groups. And so you cannot hear the shape of the drum, I guess. Not in the strongest sense, but maybe in some small sense. Maybe within some class there are only finitely many, I don't know. These are all interesting questions. Yeah, yeah. If we look at what?
If we look at flags of subgroups, we get multi-zeta functions.
I guess you could. Yeah, you could do that. That's, I don't know whether some people have studied that. So the suggestion is to, instead of counting subgroups, to look at flags of subgroups, let's say flags of length 2 or something, and then develop some kind of multi-variable.
Do the values correspond to multi-zeta functions?
I don't know.
Okay.
I don't know. I mean, you would get something. I mean, you could compute it, yes.
Has something to do with the degree of this fundamental growth?
Yeah, so, okay, I didn't get, so there's no analog of this bus. There's no analog of this bus result. We don't know, even in the nilpotent case, we don't know what the abscissa is, but there are some bounds. So the bounds, this come from Lie theory, so I may be able to indicate. So it's known something like this. So h over 6, so there's a local version, but in the global version, I guess it's the Hirsch length somehow. So this alpha of gamma is somehow bounded linearly in terms of the dimension of the group. So the Hirsch length is something like the dimension of the group. And the dimension of the group is not quite true, but it's related to the rank in some sense. So it's like the rank of for the pro-P setting, kind of it's the rank of the uniform powerful subgroup that sits inside. So there's some connection. But the bounds are kind of bad. So
Commensurable groups may not have the same degree?
Yes, also this is a very strange phenomena. So alpha of Z is not the same as alpha of the infinite dihedral group. So, but this seems to be a singular example in some sense. So it could be that this is, I mean, there's only one silly reason and we just don't know why. But in general, it can jump by 1. It can jump by 1. So there's a bound. So, so if you go up by finite index, then the subgroup the degree of polynomial subgroup can jump by 1 at most.